Good morning and welcome back to the course. So at the moment, what I want to do is I want to shift to a new case study. And the case study is the use of the ATP biological battery. And the particular context that we're going to explore this in has to do with phosphorylation. So I'll come back to the battery thing in a second, but let me talk about a particular reaction. So what I want you to imagine, well, first of all, I just want to reiterate that the notion of the ATP biological battery is very much like the outlet in the room where I'm sitting. And what I mean by that is that we have this universal energy source. I can plug all sorts of different devices into the outlet, and all of them will run off of the energy that's delivered in the form of a potential difference. So, and that's done somewhere else by burning some sort of fuel. So that's the deal. Here, the fuel that's going to be burned is this imbalance, this out of equilibrium ATP to ADP ratio. That ratio is held at a fixed value, and that fixed value does not correspond to the value that those concentrations would take if the ATP and ADP and phosphate were in equilibrium. There was a quip made in, I think it's a book by Nichols and Ferguson, Bioenergetics 3, I think, where they point out rightly that we could have an entire Pacific Ocean of ADP, ATP, and phosphate, and if they were at their equilibrium concentration, they would be worth nothing in terms of an ability to deliver work. I meant to say the other day that there's this profound idea that came from Carnot about how to get work out of two different thermal reservoirs at different temperatures. And so you might remember that there is a maximal amount of work which is delivered, which is related to the ratio of the two temperatures. And the thing that I want us to observe about most of our thinking in biology is that the reactions that take place are isothermal. So it's not, in a Carnot sense in that way, that the two reservoirs are not held at different temperatures, but the two reservoirs, if you like, are held at different chemical potentials. And that is what we're interested in trying to exploit. So one of the parasitic reactions that can feed off of the ATP ADP ratio, the potential of that, is a reaction like the one shown here, where I want you to imagine this box as my Eppendorf tube or whatever. It could be an in vitro biochemical experiment. It could be the interior of the cell. And I have an enzyme E, and it can be phosphorylated to achieve the state E star, where you see the phosphate is attached here. And there's a reaction, a forward reaction, which I will write down as E plus ATP goes to E star plus ADP, and the rate constants here are K1 and K minus 1. And then there's a second reaction, and that second reaction is of the form E star plus PI. Oh wait, what am I saying? I said this wrong. E star goes to E plus PI. And this one, the forward rate is K2 and the backward rate is K minus 2. So I'm going to refer to these two reactions as star and double star. And coming back to my diagram, so let me label these guys. So the forward rate was K1, the backward rate was K minus 1. Here, this rate was K2, and the backward rate was K minus 2. And what I want you to observe is that the way we've drawn this, we've drawn the arrows in such a way that you're supposed to get the idea of a net cycle. In other words, there is a one-way flux. This thing is in a so-called non-equilibrium steady state. It's constantly churning, and every time that one reaction cycle takes place, there is a consumption of an ATP. So there's an ATP hydrolysis event. Now, the significance of the pumps that I show you on the perimeter, the edges of the box, are we're going to maintain ATP, ADP, and phosphate in a non-equilibrium steady state. And so every time an ATP gets consumed, a new one will be pumped in. Every time an ADP is produced, one will be pumped out. Every time a phosphate is produced, one will be pumped out. And so these pumps are basically serving the purpose of maintaining the ATP biological battery. And what I want to do now is I want to calculate the net flux, the net cycle through this reaction. So to do that, what we'll do is we'll write down a kinetic equation. So I'm going to say that dE by dt, and I should just say by conservation, that's the same as minus dE star by dt. For every E that's created, an E star has to be destroyed and vice versa. And now I can write down the net. So I have a minus K1 and then an E, and I'm going to use the notation C subscript ATP for the concentration of ATP. I have a plus K minus 1 and then an E star times a C ADP. I have a plus K2 E star, and finally I have a minus K minus 2, and that one is E times Cp. So that is the fundamental governing kinetic equation. I should note that, as I mentioned already, that there's a constraint, and that constraint is that E plus E star is equal to a constant, which we will refer to as E tot. So the total number of enzymes in play is fixed. And if we convert, as I said before, an E into an E star, then that means E goes down by 1 and E star goes up by 1. And the net change is 0. So these two equations, I could call this one 1 and call this one equation 2. So our goal, first goals, find the steady state E and E star. So I want to know those two concentrations. And then given those, I want to find the flux, the net flux. So just as an observation, so reaction 1, the net, is going to be equal to J1 E goes to E star, and then minus J1 E star goes to E, and I can write those by looking at our equation. So the right pointing, this one, is going to be K1 E times C ATP, and this one is going to be K minus 1 and then E star C ADP. So I want to compute the net flux. I will also note that J2 net is going to be equal to K2 and then times E star and then minus K minus 2, and that's E times Cp. So those are my fluxes, and because this thing is in a so-called non-equilibrium steady state, I have that J1 net is equal to J2 net, and that corresponds to the observation that the flux along this path and the flux along this path are equal. It's in steady state, meaning that the number of E's and the number of E stars is fixed. But it does not mean that there is no dynamics. There is definitely dynamics. These reactions are running back and forth, back and forth, back and forth all the time. But the net is that there's more flux from E to E star on this pathway and then more flux from E star to E on this other pathway. And they're balanced. So that's what we mean by this non-equilibrium steady state. So I said that our goal is to find the steady state values of E and E star. let's take a look at what I mean by that. So find steady state. Steady state means that dE by dt equals 0. And I can rewrite that condition. I need to add a page here. I can rewrite that condition as follows. From above, note what I have here. I can isolate on one side these two terms, and since this and that have minus signs, I push them to the other side because this total thing is 0, and what I'll be left with is, so I have K1 and then E times C ATP, and then I also have K minus 2 E, and that gets attached to a CP, and that's going to be equal to, again looking up here at our equation, that's going to be equal to K minus 1 E star, K minus 1 E star C ADP, and then plus K2, and that's just going to be E star. So that's our condition of steady state. And now what I can do is I can use the fact, so now use that E star is equal to E tot minus E, substitute this here and here, right? So if I plug in E star as written there, what I will be left with, conclusion, is that, so what am I going to do? When I substitute this in, note what happens. I'm going to pick up an E tot times K minus 1 ADP, and then this K2, and then I'm going to also pick up with a minus sign these same coefficients, but times an E, and so I can bring them to the other side. And so what I'm left with is, I'm just going to write it down by inspection, I'm left with E steady state is equal to K minus 1 C ADP plus K2, and then divided by what really amounts to something like a partition function. So I have K1 C ATP plus K minus 2 CP plus K minus 1 C ADP plus K2, and this is all multiplied by E tot. So that's the steady state value of E. Now I know that E steady state plus E star steady state has got to be equal to E tot, and hence that means when I add E to E star, the numerator and denominator of this big thing have got to cancel out, and so straight away I can see that this implies that E star steady state is going to be equal to K1 C ATP, and then plus K minus 2 CP, again over the same denominator. So we'll take that denominator, we'll plug it in up here, and then we multiply by E tot. So we have found what we sought to discover, which is the steady state values of E and E star. So what do I learn from this? What I see is that the steady state values, like just for example, look at the numerator of the second guy. If I ramp up the concentration of ATP higher and higher and higher, what I'm going to do is I'm going to drive the production of E star. The steady state value will be higher. Now let's next work out the net flux Okay, we already have written down an expression for the net flux, which is given by this. Okay, so maybe I'll take this expression downstairs and we'll plug it in. So I want to find this steady state flux. How do I do it? You can see what I'm going to do is I'm going to use this result and this result, and together they will give me the net flux. So let's have a go at this. So this thing is going to be equal to I have K1 C ATP, and then I multiply by E steady state. So that means I need to take this quantity, which I will put here in parentheses, and then I subtract minus K minus 1 C ADP, and then here I need to take the numerator of the E star, which I will do now, and bring that down. It's getting kind of crowded. And then all of this is divided by this common denominator, which I'm going to just continue doing cut and paste. So I take this denominator, and finally this gets multiplied by E total, which I'll put in front so I don't have room over on the other side. So that's the net flux. Now what I want you to notice is that two of these terms cancel each other. So this term and this term cancel each other. How do I know that? Because there's a K1, K minus 1, ATP, ADP, K minus 1, K1, ADP, ATP. And so the net result, when all of the dust settles, is a net flux of K1, K2, C ATP minus K minus 1, K minus 2, C ADP, CP. This is all divided by that same denominator. And then I have this E total factor. Yeah, so that's very interesting, and insight. It leads to a lot of insight. And the reason I claim that is, first of all, let's look at what happens when the net flux is 0. So net flux 0, that implies that this numerator is 0, which tells us that K1, K2, C ATP minus K minus 1, K minus 2, C ADP, CP is equal to 0. Or, said differently, I have that C ADP, CP over C ATP is equal to K1, K2 over K minus 1, K minus 2. Let's think about units for a moment. So units, just to make sure we're all thinking about this correctly. If we go back to our kinetic equation, written up here, notice that, okay, first of all, the left-hand side has units of concentration per time. This is concentration per time. That means all 4 of these terms on the right-hand side have to have those same units. Hence, K2, this one, has units of 1 over time. But all the others, K1, K minus 1, and K minus 2, have units of 1 over molar, 1 over seconds. as often we see when we have a second order reaction. So that's just to point out that, here the net units on the left side are concentration, and the net units here, because of what I just said, are also going to have concentration. The reason being that K2 is the thing we said had units of 1 over seconds. This has units of 1 over molar seconds, 1 over molar seconds, 1 over molar seconds. And so the net is molar units. I also am going to, in general, I'm going to multiply both sides by 1 over C naught to render this thing dimensionless. C naught, you'll remember, is our standard state concentration that showed up in the context of our chemical potentials. I will talk about that in the next vignette when I talk about the energetics of this reaction. For the moment, what I'm doing is talking about the flux. Okay, the next thing I want to point out, so first of all, we've commented on steady state, equilibrium. When there's no net flux, this condition is met. And this basically corresponds to detailed balance, I would also note. But when the drive is sufficiently large, then what we see is that the net flux is positive. That means this reaction is going to the right and circling around. And every single reaction costs 1 ATP hydrolysis. In the language of chemical potentials, what I mean by that is that every reaction leads to the destruction of an ATP and the production of an ADP and phosphate. And in the spirit of this figure that I showed you, what we're going to imagine is that in order to keep the ATP battery charged, we have to, because we consumed 1 ATP, we have to put a new one in. Because we produced an excess ADP, we have to send one out. We produced an excess phosphate, we have to put one out. And so that's the net reaction in order to keep the battery charged. And again, there's a net flux around this circuit. There's a net dynamics, which is really interesting. And we only get that, as you can now see, by pushing the reaction out of equilibrium. So again, I'm focusing on this denominator, and I'm just noting if I ramp up ATP higher and higher and higher and higher, then the consequence of that will be that J gets ramped up higher and higher and higher. So basically, this ATP battery can be tuned. If you like to think of it as a voltage, then the voltage of that battery, this is an analogy, I don't mean it actually seriously, but the voltage of that battery can be increased from 1 volt to 10 volts or whatever by monitoring, by tuning up this and tuning down the ADP, for example, or said differently, by increasing the ATP to ADP ratio. So what have we accomplished here? This is the first of 2 vignettes that I'm going to offer about the ATP battery. And what I wanted to show you was, given this universal battery, if it's maintained at a fixed value, it can be used to drive parasitic reactions once again. And I note once again that this is another version where the key element is coupling. When I was talking about the symporter, I referred to this notion of coupling as implying that the membrane protein was an AND gate. And the same thing is sort of true here. The enzyme cannot go from an E to E star in the absence of coupling to the ADP. ATP goes to ADP process. Similarly, the E star can't go to an E unless it dumps the phosphate. So that's the first round of thinking about the ATP biological battery. What I'll do in the next vignette is I will talk about the energetics, which is already shown here in this particular slide under parts B and C, but I think you'll be highly amused by that.